Hello students, welcome back to the Tantray physics classes. Today's lecture is on circular motion, that is third lecture. Therefore, I am discussing right now banking of roads. Why we need to bank the roads? For safe passage of the vehicles on the circular roads. And with a few examples, and this is the third lecture on circular motion. So, banking of roads. Banking of roads. Banking of roads. Banking of roads. So, first of all, I must tell you why we need to bank roads on the circular tracks. Because we need a force. On a circular track, we need a force towards the center of that circular track. The point is, who will provide that force, centripetal force, for a vehicle to be moving on a circular path? For that, there are two possible ways. One is frictional force on the road. That also helps. Frictional force also helps for the vehicle to move on a circular path. Second is, if this frictional force is not sufficient, if we assume that the road is smooth, then we need to bank the roads so that the component of the normal reaction, the road gives normal reaction, the part of that normal reaction, the component of that normal reaction should provide the necessary centripetal force to move the vehicle so that the vehicle negotiates a circular track. That's all. So suppose this is a road. If I make the road like this, have a look. Suppose it is the road. Here the road is coming out from the board like this. This is the road. This is the road. This path is the road, and the vehicle is on this road, and it needs a force towards my head. Center of the road is towards my head. So I need a force in this direction. Towards my head. And if the vehicle is here on the road, the normal reaction is upwards, vertically up. The component of that normal reaction towards me is 0. Therefore, no component of the normal reaction will provide the centripetal force. So the road has to be like this. So that the vehicle on the road, this is the normal reaction now. This normal reaction has two components, one like this, other upwards. The normal reaction, the component like this, will provide this necessary centripetal force. So if the road is like this, is the road coming out. It is not road like this, it is road like this. And the vehicle is here. Coming like this, and mg is downwards, normal reaction is upwards, and this road is like this, horizontal but curved, and I need a force in this direction, centripetal force, that is mv square by r. But what is the component of this normal reaction in this direction? That is 0. So this force is not going to be provided. So the vehicle will move in a straight line. It will not move in arc, because force, it needs to move in an arc, we need a force towards the center. So no agent is providing this force. So obviously the vehicle will not move in arc, it will move in a straight line, and that straight line will not have a road, and it will stick it off. So in order to negotiate the roads, we need to bank the roads. So what we need to do is, this is the horizontal road like this. It needs to be banked like this. And now the vehicle is not here on the plain road. It is on the banked road like this. It is not moving like this or this. It is moving like this. It is the road, banked road like this. And mg is downwards, gravitation. And this is normal reaction. And this is also theta, If this angle theta, banking angle is theta, this is also theta. If this is theta, this is also theta. This normal reaction will split into two components, n cos theta, and it will be like this, n sin theta. So I needed force towards the center O, so towards the center of that circular road O. If the radius is r from here to here of the circular road, so yes, I have the normal reaction component of the normal reaction provides the centripetal force. So F is equal to ma, mass into acceleration, that is Newton's law. But this force is the agent. Who is the agent? Agent is now n sin theta. And this provides the centripetal acceleration. What is centripetal acceleration? A, that is v square by r. So this component of the normal reaction provides us the centripetal force. Now the car will negotiate the curve safely because the force has been provided towards the center of that circle. Okay. Now what balances the n cos theta component? That is being balanced by the weight mg, that n cos theta is equal to mg. Right? Now if I divide these two equations, like this and this, what I get is tan theta is equal to m gets cancelled, v square by rg, or theta is equal to tan inverse v square by rg. Yes, this is the banking angle. This is the banking angle. So the engineer set the banking angle for the given speed. And that's why whenever there's a curved road ahead and there's a warning written there, there's a curved road ahead, drive slow. So you can, if you are faster, then possibly that angle will not be sufficient for your moving on the curved road. Suppose theta is the angle for a given velocity. Maybe 40 kilometers per hour, yeah, or 50 kilometers per hour. There will be some radius of the arc of that road. G is there, G is 10, and you calculate the value theta. The engineers calculate the value theta for that banking angle for a given speed, for given r, and G is given to be 10. Okay. Now, if you move at a speed greater than that speed, what is going to happen? Suppose this is the road and you are moving in a car and banking is theta. You are moving at a speed greater than the allowed speed. I mean, theta has been adjusted for a given speed. Like, let me suppose 40 km per hour, but you are moving at 70 km per hour. So if you are moving at 70 km per hour, theta is fixed there. So you will move in a radius of greater radius. You will move in an arc of greater radius. You will move in on a road having a radius which is greater than this r, because you are increasing speed. So r will also increase, so that theta is the same as it is. So you will move in a circle of greater radius, and there is no road there, and you will stick it off the road, away from the road, outside. So if you move at a speed greater than the speed allowed, because at that speed theta has been adjusted, but you are moving at a speed greater than that speed, so r in the denominator will also increase. So you will move in a circle of greater radius, and finally you will stick it off the road, on the outer side of the road. So this is what you call as banking angle. So the roads are banked so that you can safely negotiate the curved road. That is all. Okay. Now, example number 1. First example. A road has a circular turn of radius. A road has a circular turn of radius 10 meters. Is banked road, a road has a circular turn of radius 10 meters, is banked at 10 degrees. Find the speed at which the vehicle on the road should move to negotiate the curve, the turn safely. That means what should be the speed of the car so that it moves safely on the road. The road has a banking angle of 10 degrees, and the radius of that road, circular road there, is 10 meters. What should be the speed? We already know the formula, that is tan theta is equal to v square by rg. Right? Now, what is v square? That is tan theta rg. What is v? That is root of, yes, I will write rg first, rg tan theta. So what should I write? That is, r is, okay, 10. What is g? That is 10. And what is tan theta? That is 10 degrees. Right? It is 10 outside, 10 and 10 outside, 10 degrees. It is, when you multiply it, is 4.2 meters per second. That is all. To multiply, substitute this value, it is valued to 4.2. Okay. Second example, that is, second example, a circular track of radius 600 meters. A circular track of radius 600 meters. A circular track of radius 600 meters Yes, a circular track of radius 600 meters is designed for cars at an average speed of 180 kilometers per hour. What should be the banking angle for the track, for the circular track? What should be the banking angle for the circular track? For the circular track. What should be the banking angle for the circular track? This is a road on which a car moves, and this road is curved and it has a radius of 600 meters, and you need a force towards the center O, that is mv square by r force. This you need, but there must be real agent for that. That is the normal reaction. That's why the banking normal reaction. That's why the banking is the road is raised from one side. That's why the banking has been designed. And this part of the normal reaction. If the normal reaction is like this, there's no component in this direction. So normal reaction has to be like this. So road has to be tilted a little bit so that this normal reaction has two components, this and this. This one toward the center gives the centripetal force. But we already know the formula, but that has been done. Okay, now what I do is, yes, first of all, this speed, I will convert it to meters per second. So speed is equal to 180 kilometer per hour. That speed is equal to 180 multiplied by what? Yes, 5 by 18 meters per second. This is a rule. If you want to convert kilometer per hour into meters per second, you just multiply by 5 by 18. If you want to convert meters per second into kilometer per hour, you multiply by 18 by 5. Reciprocal of this. Okay, now this cancels off. So V is 50 meters per second. This is the speed. So what I have to find? I have to find the banking angle. And you already know the formula. The formula is tan theta is equal to what? V square by RG. That is the formula that we developed just now. Now, what is tan theta? That is equal to, yes, that is equal to, what is V square? That is 50 into 50 by what is R? 600. What is G? That is 10. 2 zeros cancel, and it is 25 by 60. It is 5 by 12. So theta is equal to tan inverse 5 by 12. That is theta is equal to tan inverse 5 by 12 is what? 0.4. Something like 2, yes. 0. Now theta, if you convert this into degrees, that is theta is equal to 22.4 degrees possibly. Yes, you will check it out. Check it out when theta is equal to tan inverse 0.42. Check it out whether it makes 22.4 degrees. Answer. I have discussed banking of roads with 2 examples. You just do it, but don't forget to subscribe to my channel due to Tantray sir physics classes, and don't forget to download my app Tantray sir physics class, which you can download from the Google Store. Thank you.